All right, let's begin. Heavenly Father, we thank you for this afternoon. We thank you for your creation, that we can study, that we can understand it, that you've made it so we can understand it. We thank you that you revealed this mystery to us, that we can have some control over nature as you have so designed, Lord. We thank you for that. Pray that you help us to understand just a little bit more about gravity today, and I just pray that you continue to encourage the students to work to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so I have a few gravity examples for you guys, and then I'll take homework questions. I think there'll be time left over. So let me just get started. My first example will be this one. Earth. All right. And then, I don't know, Superman, Batman, your pick.
Superman.
All right. There you go, Superman. He's in disguise. Here. Put glasses on him. But he's Superman. And suppose Mr. Superman here, he throws a ball, mass m, with velocity v naught. All right? So he throws this ball with velocity v naught straight up from the surface of the Earth, all right? The question then is, neglecting, just imagine that the Earth isn't moving, or if you want, neglect the orbital motion of the Earth around the Sun. And the question is simply this: does the ball come back? Now, before in this course, the answer was yes, right? It's got so much kinetic energy at the start. Once that kinetic energy is equal to mgh, it's got zero kinetic energy, and it comes back, right? But that's no longer the case if we analyze things in view of the real potential energy function due to gravity, right? So what's the potential energy function at the start? What's energy here? Yeah, E naught equals 1/2 m v naught squared, and then what? Plus the potential energy due to gravity, right? So we can say plus g m, mass of the Earth, right? Divided by what? Radius of the Earth. And that's not quite right because it's a minus, right? So remember, the force of gravity in the radial direction is minus g m me over r squared. And so that's equal to minus the potential energy differentiated with respect to r. That implies then that the potential energy as a function of r is something like some constant minus g m big M over r. Because if I differentiate that with respect to r, I get gm m over r squared, but then we multiply by minus because that's the relation of potential energy to force. Now, if you look at my notes, I explained that this is actually part of a larger three-dimensional idea. In principle, you look at spherical coordinates and take the gradient. But the thing about the gravitational force is it has no angular dependence, so the possible terms which would arise from the polar and the azimuthal angle, those are negligible here because there's no such dependence in the force. So the potential energy is completely a function of the radius alone, like so. And then to set that constant equal to 0, that's one option. That's what I do, all right? And there you go. That's the kinetic. That's the total mechanical energy to start with, right? So, what would it take for it to be able to turn around? What would it if this goes all the way up, right, to some turning point? I mean, my picture's not to scale, right? I mean, we're talking about Batman or Superman here, so you got like, I don't know, like the distance to Mars or something, right? I mean, it's a ways out there, right? Whatever. The point is, there would eventually be a place where what? If it does turn around, there would be some place where VF is equal to 0, right? So what could you do? You could try to solve this, right? You could say, is there a solution, question mark, to minus g m mass of the Earth divided by that, maximum r. Let's call it r max. Now that'd be the distance from the center of the Earth, right? This r max. So I guess to be fair, I should really say radius of the Earth plus the altitude there. That's more interesting. Now, this question is the same as what question? This is the same as the question, can you solve 1/2 m v naught squared equal to g m m e, right? Times what? Times 1 over the radius of the Earth minus 1 over the radius of the Earth plus h, right? Does there exist a solution to this?
Why did you say minus? What did the altitude? No, because it's minus g
Algebra, yeah. Right. Let me draw a graph of what's going on here, all right, and show you why there won't be a solution always. This is if I'm going to graph potential energy, right, versus R, it's then minus the reciprocal, right? So it looks like this, right? The most the potential energy due to gravity can ever be in this current setup is 0, right? If your net energy is like this, if this is E naught, well, there is some, this is the radius of the Earth plus h right there. That's the R, where it turns around. That's where your potential energy is all of the energy, and the kinetic energy is 0, it comes back. But if your velocity is so fast at the start, right, that it's up here, right, do it in red. If your initial velocity is so fast that your energy is up here, you're going to find that equation has no solution. Right. That doesn't mean physics is wrong. It just means that what you're looking for doesn't happen. It doesn't turn around. It just keeps going. Let's see here. What is the energy that it just barely escapes? If you throw it straight up like this. Well, anyway, what's the escape? Would it be what? When E naught's equal to 0, right? That's just on the cusp of things here. So that would be what? When you had what? 1/2 m v naught squared equal to g m, excuse me, s of the Earth divided by the radius of the Earth. So what is that? We cancel the m's, right? And we get v naught something like the square root of 2 big G, mass of the Earth, divided by the radius of the Earth. Let's see here. What's that? Let's figure it out numerically. That's 2 times 6.67, 3, times 10 to the minus 11, times about 5.9 times 10 to the 24th, divided by, what was it, 6.37, something like that, times 10 to the 6th. All of that meters per second, right? Excuse me. Let's crunch the numbers, see what we get. I mean, you might worry. You go outside and play with a baseball or something, throw it too hard and never come back. I mean, that'd be sad. Something you gotta worry about, right? Well, it's not something we have to worry about, I suppose, but maybe if you're Superman. In my ballpark for the 5.9, I know there's more digits that we can look up for that, and we might need to. for a web assign problem, right? I get in my current numbers about 11.11, well, I guess 11.12 kilometers per second. Or if you like, 1.112 times 10 to the fourth meters per second. Yeah, it's kind of moving. How many miles per hour is that? That's kind of what I think in. See, if I divide by 1609, that gives me the number of kilometers per second. No, that gives me the number of miles per second. And then I do what?
Multiply by 3600.
Yeah, multiply by 3600. If I did this right, whoa. Is that right? I'm always a little bit leery of when I do unit conversions in my head. I like to see the ones cancel, you know. But if I'm right, that's 24,876 miles per hour. Whoa. So yeah, I personally can't throw a baseball that fast, so I haven't lost any in this way. But if you were Superman, you know. Well, yeah, as you've seen, I mean, he's wants to throw people into the sun and junk, right? So that's part of it, you know. So a popular question on a final for a physics exam is something like, I mean, you could play other games, right? Like, you're on a mystery planet, you're Superman, you throw balls straight up. You find that when you reach a certain velocity, they don't come back. What's the mass of the planet? If I gave you enough other information, you could figure that out. See? Because this relates the mass of the planet to the universal gravitational constant, to the radius of the planet, to the velocity of a projectile that you're starting with, right? So, yeah.
So we need to know the radius too.
Yeah, at the moment.
So that's like,
What's that?
why is the energy equaling zero, like energy not equaling zero, the escape energy?
Why is what?
Why is E not equal to zero? Why is that the escape energy?
Well, because if we look at the energy level diagram here, right? This is the potential energy, right? So if I graph kinetic energy plus potential energy, that's constant because energy is conserved. So if you just look at what's possible, right? I have to be above the potential energy graph, which is the black thing here, right? So, you know, if I'm above this level, and that's like my energy level, the red one, then I never get pushed back by this because this is at most zero. The minimum kinetic energy I ever have is like this much, you know? That's the minimum kinetic energy I have, that much. And I have even more kinetic energy like over here, right? This corresponds to what we know about orbits for planets, right? As the planet gets closer to where the gravitating body is, it gets faster, and as it gets further away, it slows down because, you know, that's got more potential energy out there. Well, you know, in this case, you've got so much kinetic energy that you're not even gravitationally bound, so you just keep going. Yeah.
So if escapes and if it's negative, it doesn't.
In our current setup, yes. If I changed the zero of the potential energy, it could be different, right? So that's all because I've set this constant to zero is what's causing us to say these things. Yeah. So, yep. Now, I mean, there's other ways to give you information about the mass of the planet, by the way. I could tell you something about the acceleration due to gravity, right? That also relates to the radius and the mass of the planet, right? If you knew something about the acceleration on the planet, that would also give you information about because what's the acceleration due to gravity on the planet? Remember? G planet is what? Big G, mass of the planet, right? divided by the radius of the planet squared. Because the force due to gravity on the planet, on the one hand, is defined to be your little mass, right, times the gravity on the planet, whatever that is. But on the other hand, by Newton's universal law of gravitation, it's big G, mass of the planet, little m, divided by the radius of the planet squared. So if you look at this and you cancel the little m's, you get that the gravity, the acceleration due to gravity on a planet is related to the universal gravitational constant, that 6.673 thing, the mass of the planet, and then the radius of the planet squared. So it's, if I have two facts, both of which relate to the gravity, the mass of the planet and the radius of the planet squared, that will be enough information to figure out both the radius of the planet and the mass of the planet. That goes for Earth just the same, right? Maybe if you're a 17th century ship, person sails around the sea or whatever, maybe you studied ships sailing off into the horizon enough that you have a sense that the Earth is curved. And if you think about it long enough, maybe you could figure out what the curvature is and extrapolate back what the radius must be. If you could do that, and you understand Newton's law of gravity, you could extrapolate then what the mass of the Earth is. Right? These things are interconnected. So that's one example. Here's another example. And this one's a little bit different. Suppose you've got a mass here, m, and then you've got this rod, like so. Total mass big M. Uniformly distributed. All right? The question then is, what's the gravitational attraction of the rod on the sphere up here? Find the force of gravity on little m due to big M. Now I can't just use Newton's universal law of gravitation. Why? It's not a sphere, yeah. And you might worry that, well, I guess you could just be like, well, you can just look at the center of mass, right, and do it for there. I'm not sure. Well, we'll find out if that's right or not. But we can derive this from the superposition principle, all right? And the superposition principle just says what you do is you take this rod and you chop it up into pieces, like so. And I guess we need to know this distance. What do you guys want to call this? Let's call it L. All right. And let's call the distance from the top of the ruler to this little bit of mass dm, let's call that x. You want to call it y? We can call it y if it makes you feel better. X is fine? All right. Or y is fine? Either one? So you're telling me yes. Okay, I'll accept it. I'll accept it. Could be worse. My children have been accusing me of liking Minecraft lately. I'm like, I do not like Minecraft. I mean, I love Legos, but I don't like Minecraft. I don't know. Can't get into it. I mean, it's kind of weird. These kids are like eating pigs or destroying pigs, and there's like these creepers and there's these zombies, and there's only 128 blocks. I've learned. I don't know. I feel like I'm going to have to spend a couple hours playing it so I can understand the youth, but I don't know.
Do your kids play?
Oh, yes. They're only allowed 20 minutes, though. So, after they've done their various chores and such. Actually, they have a choice. They can either play the 20 minutes of the Minecraft on the iPad or whatever, or they can play my daughter got a Nintendo DS from 15 years ago. My wife got it on eBay for cheap. And you play 20 minutes of that, or you can play 20 minutes with Mom's phone. My phone does not have games. Although I've been meaning to put Angry Birds back on it again. It's important for faculty meetings. But what I really need is some of those noise-canceling earbuds for graduation. That's what I really need.
They have ones without cords now.
Yeah, they have Bluetooth ones now.
Really?
Yeah.
Ooh. I may never have to listen to a commencement speaker again. Woohoo! See, you guys graduate, but I never do. Anyway, so the point is, there's a little bit of gravitational force that comes from this dm, right? You could think about it as like being a little df. A little bit of gravitational force. And what is that df? df is, it's downward. I'm just going to look at the magnitude, if that's okay with you guys. G, little m, dm, and maybe I should say d big M, just to be clear where it's coming from, right? It's not a little bit of the little mass, it's a little bit of the big mass. Divide by what? The distance, which is x plus L squared. All right? Now, I guess I should also tell us we should also characterize what's the length of the rod, right? So x goes from x, 0, less than or equal to x, less than or equal to what? Let's say that the length of it is capital L, all right? So this would be good for 0 less than or equal to x, less than or equal to L, where L is the complete length of the rod. Now, I don't know about you. I don't know how to integrate dm like this. This is a heuristic to set up the calculation. What is actually dm? How about this? Dm over dx, that's the instantaneous rate of, that's the mass per unit length, instantaneous mass over the instantaneous, not instantaneous, over the infinitesimal length, dx, right? If it's a uniform mass density, that's the same as the total mass divided by the total length, which is what? M over L, right? This is uniform. Yep.
What is big L?
Big L is the total length
Of the stick?
of the stick, yeah. I should probably use some other letter. Oh well. Okay, so we got what? We got G, little m, over x plus L quantity squared. And then big M over L times, well, dx. See, I can solve this to get dm is m over L dx, right? I'm going slow here because you guys have a lot of trouble with this example when I put it on a test. A lot of trouble. Lots of trouble. A significant number of points are lost on this problem. You got it? Okay. I missed what you said. What did you say? Oh, no, I was not talking about your suckedness. I was talking about the suckiness of past physics courses. Not you guys. You guys are better than them, right? You are clearly better than them. You have not filled out my course evaluations yet. So. Sorry. I digress. No, I don't know, guys. You lived in a world without word problems, and with just a hint of calculus, and then all of a sudden you're thrust into this course, which has both word problems and calculus, neither of which you're comfortable with. And then, oh, by the way, I'm going to test you on problems that we haven't done yet in the test. So yeah, I mean, it's no wonder you guys have trouble with it. But it is the nature of physics. So, what can I tell you? So there you go. That is something I can integrate from 0 to L, right? And that should give me the force. Well, can you integrate that? So I'm going to pull the constant, which is G, M, divided by L. Pull that out. That's a constant, right? And then I'm integrating from 0 to capital L of dx over x plus L quantity squared. No, the reason I make that comment is just to alert you to the fact that, like, some of you, like, you see me do something, right? And it might seem like you understand it, but you have to ask yourself, if I go back, I write down the start of this example, right? And then I ask myself to derive it following the thought process that we went over just now. Could you do it? Not looking at your notes, right? If you can do that, then you really understand it. If you don't, well, like so many used car salesmen have tricked you into thinking you understood something you didn't. Which is good teaching, right? No. I don't know. I had this one professor who taught a certain course, and like he'd finish a lecture and I'd be like, man, I understand so much, and then I like just try to do something in it, and I'd be like, oh man, that guy is such a, I was tricked. I don't understand anything, man. I think that the integral of 1 over x plus L squared is just minus 1 over x plus L. Do you agree? If I differentiate this thing, do I get back 1 over x plus L quantity squared? Right. You can make a u equals x plus L substitution if you want. And then plug in the stuff. And you got minus 1 over L plus L. I regret my choice of L. Plus 1 over little l. I'm going to continue this up here. So what we got is we've got g m over L, and then if you make a common denominator here, what do you get? You get L plus little l minus little l over L plus L, right? Times L, making a common denominator. The L's cancel. Which L's? Both of them do. They additively cancel upstairs, right? Once those are gone, then you're left with big L over big L, which cancels, right? And what's the answer then? You got we get ourselves a g m divided by little l times big L plus little l. And there you go. That is the force. That reminds me, I need to buy The Force Awakens today. I've been told I should rent it, but I feel like we're going to watch it enough times. I should just buy it, you know? I don't know. What do you think?
Yeah, I'd say you're pretty young enough.
I mean, how many times you got to watch it? Like, oh man, I've only got I've only got smudgers. I don't have erasers today. I'll be right back. I got to get it. This bathroom is old. It should still have actual. We should actually, there's no need to stop it. I'm just getting paper towels. Sometimes people feel an obligation to cut it off when I go to the bathroom. It's okay. All right, that's my second example. Now on to the third example. Any questions about that one? How could you make this more fun? You could ask you could put another rod over here. And then ask what's the force of gravitational attraction due to 2 rods at once. For example. Mwahaha. Mwahaha. I won't do that though. Well, not today anyway. I gotta save something for the test. Too soon? Maybe too soon. I think it's always too soon. Let's see here. Another example, popular example, something like this. I'll try to keep this fast. I've got, just to keep it simple, 4 equal masses, like so, on the edges of a square. And what do you want the side length of the square to be? 1? I'll take that 1 and raise you an r. Then the question is simply this, and I'll pick one, say this one. Find gravitational force on M due to other 3 masses, 3 M's, right? And then magnitude and standard angle, let's say. All right. Let me label these. Let's say that this is 1, 2, and let's say that this one is 3. All right. So let me just draw the so like you've got a force of attraction like this, right? Let's say F1. You have a force of attraction like this. That's F2. 3 rather. Sorry. But then F2, which way does that go? Right. Like that. Now, F1 and F3 are equal, right? In magnitude. F1 equals to F3 equals to what? We got G, M divided by what? What's the distance here? R? Yeah, I have to square it. Exactly. Distance here is R. Distance there is also R. So I have R squared here. That's the force of the 1 and the 3 force is just that, magnitude-wise. What's the force of 2, though? So GMM, again, right? What's this distance? I heard square root of 2. I like that. This is square root of 2 times r, right? Because r squared plus r squared gives me 2r squared. Square root of that is the length of the hypotenuse. But then you got to square it, right? So that's what? 2r squared. All right. Now I have to mind the geometry, right? So here we go. The net force is what? Well, let's see here. I'm gonna just draw them separately. So we've got, of course, we have F1. It's x minus F1 though, right? Let me just get straight to the point. Minus GM m over r squared, 0. This is from 1, right? And then plus what? 0 GMM over r squared. This is from 3. And that's not right yet. Why is it not right? Gravity's attractive, right? So 3 is pulling the top mass down. I need a minus there, right? Many of you could improve your score by a letter grade if you paid attention to these minuses. I know, silly, but true. All right, now this one, F2, well, that one I got to think about. This is 45 degrees, right? So fun fact, cosine 45 degrees is sine of 45 degrees, also known as 1 over root 2. Right? Yeah, is there a question? Oh, okay. Just relaxing. It's all good. Now, how about the... Looks like it's like a Bernie Sanders campaign, right? It's all negative. Let's see here. Oh, I'm sorry. I forget. You guys feel the burn. I forget. Although I once accused, I think last year I accused physics of like their generation putting Obama in power, and they said, no, we didn't. They were like, no, that wasn't us. And I was happy they reacted so violently to the accusation. It did kind of make me feel better about my day. Now, the magnitude there is 2r squared, though, right? So that times 1 over root 2. And then the magnitude, again, is gmm over 2r squared. But then I have to multiply by the sign, which is 1 over root 2. I mean, of course, the masses on the square don't have to be equal. How would it change if the masses weren't equal? Yeah, you'd have different. I mean, sometimes I'll ask this question so that I've got like m, 2m, 3m, 4m, and that spoils the 45 degrees, right? And then you add, right?
What is the sign just for the 1 divided by the square root of 2? Is there no sign of multiplication?
Oh, these are it's multiplication. Let's see here. So what I have is I've got minus 1. What? Minus 1 over 2 root 2. And then minus 1. Minus 1 over 2 root 2. All right, I don't know. Let me clean this thing up. What is that? GMM over r squared. I don't know. What is this thing? How can I simplify that? Is that just... I don't know. Fine. I guess it's 1 plus 1 over 2 root 2, right? Times the vector minus 1 minus 1. Or if you like, I like unit vectors, you know? So that's G, M, M. These are the same M's. I don't know why I'm drawing them different font. Mostly because I'm an idiot. Let's see here. 1 over square root of 2. 1 plus 1 over 2 root 2. Oh, sorry. I meant multiply by root 2. And then this beloved unit vector. Unit vector. If that's a unit vector, then this is the magnitude, since it's positive. So, I mean, what's the standard angle here? What is standard angle, by the way, guys? You measure from the positive x-axis, right? So if the force is over here like that, right, as it is, it's like that. So it's 180 plus 45, 225 degrees. There's a lot of people who aren't being careful about that right now. It's probably a half a letter grade. I don't know. Something silly like that. I mean, I'd really rather that you fix that before the final. I feel so silly to damage your GPA on something so ridiculous. I mean, in other courses, you've gotten B's or A's for things that are like, I don't know, way easier. Hardly seems fair. But, you know, it is this course. Yep.
Why did you take out a square root of 2?
Because I want a unit vector.
And that is unit vector?
1/2 plus 1/2, square root.
Because it's 1.
I mean, that's cosine and sine of the standard angle. you look at it. But, I mean, that's how I think about things sometimes. All right, one last example, then your homework. All right, so one more example we got in my system here. Now, there's two ways we can do this. I can show you the easy example and put the hard one on the test, or I can show you the harder example and put the easy one on the test. What do you guys want?
Second option.
The harder one and put the easy one on the test.
Oh yeah, go hard, go home.
Okay.
I don't want the test to be too easy. Wait, what? No.
Matthew will be in the hall afterwards for his beating. See here. Suppose you have 3 moons. Symmetrically situated in a common orbital plane. Now, you can't solve the 3-body problem in general, but you can solve this 3-body problem because it's special. It has such nice symmetry. It is in fact possible to solve it. So I intend for these to all be what? 120 degrees, right? And so they're spinning in space. Why do they keep spinning? It's because they're pulling on each other and keeping each other going in this circle. If you have, I mean, you can imagine just having 2, right? If you had 2, then they would just be, like binary stars. So I'm going straight to trinary stars per your request. All right, so the question then is if the to relate the velocity and the radius of their orbit. Well, I guess I said moon, trinary system of moons. You have to imagine this is like, what's his face there? The dude with the mask. Yeah, that one. He already destroyed the planet. It's gone. Okay. So, oh, I'm sorry. Spoiler alert. He shot the other planet at this planet and it's gone. Okay, fine, whatever. I don't know where the mass went. Don't think about that. Talking about fictional things, so the mass just disappears. Anyway, so why do they keep? What keeps? So with the thing here, whenever I have assigned this question on a test, people always get really confused because they don't understand what they're doing. And so what are we always doing in here is we're applying Newton's law, or we're using energy conservation, or we're using momentum conservation. That's most of it in here. So if you're not doing one of those 3 things, you should think about your life. What are you doing? Are you using intuition? Has your intuition served you well in previous tests? Should you be using your intuition, or should you be trying to think about a physical law that can be applied? I assure you, applying a physical law is the way to go. So you pick a mass. By symmetry, it doesn't matter which one. They're all the same, right? Just pick one. Pick one mass. And on that mass, we will apply Newton's second law. It's going in a circle, right? That means we get to do the same stuff we did last time with Kepler's law again. So which one do you want me to pick? I'll pick this one. Sorry, it was a false choice. This guy right here. No, that's the acceleration vector. I don't usually plot that. Sorry about that. So if I pick this one, right, what are the forces on this mass? I know that m v squared over r is equal to the net force because it's going in a circle. Well, at least that's equal to the what? That's equal to the net centripetal force. But by the symmetry of the problem, you can see that's all there is, right? Because what do we have? We got this and that, right? You got the force this way, and you got the force that way. And if you look at the symmetry of the problem, you can see what else? Those are equal in magnitude, right? I mean, you can't just add them. They're not in the centripetal direction, are they? How is that? Oh, there it is. So this angle here is what? I got to vote for 30 degrees. Those are both 30 degrees. I want to believe. Yeah, I believe. So let's say that this, I'm only interested then, right, in this component of it. Right, so this purple vector can be broken up into the green factor, which is in the centripetal direction, as we're interested in, and also the blue vector, which is going to be canceled out by its partner on the other one, right? Like this gets canceled out by that. If my picture was better, I'm sad. I've just quantified how bad my picture is. Like these should be matching, right? But the green doubles up, right? So you have twice that. What is that? So 2 cosine of 30 degrees, right? Times the magnitude of this force, whatever that is. What's the magnitude? Cosine of 30 degrees is what? Root 3 over 2. Thank you. So that's the square root of 3 times the force. Cosine of 30 is not a half. Cosine of 30 is like 0.86, blah, 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 blah. And such and so forth. Did you guys say a half? Them's fighting words. To use the terminology of my community college professor. All right, so probably I model my teaching more after him than anybody else, whether I realize it or not. Anyway, let's see here. This, whatever that distance is, right? Let me say d. So it should be what? G, big M over d squared, whatever that d is. Let's see here. Let me clean it up just a little bit. We already have that v squared is equal to what? Square root of 3. I guess r square root of 3. And then this g, this m, and then whatever that 1 over d squared is, right? Fill in the blank. What is d squared? If my picture is too cluttered, I draw a new one. Let's see here. So like, I still haven't, still not the right picture yet. Let's see here. That's R, right? This is D. That's 120 degrees. What's the right tool to find D with the minimum of effort here? What's that? Law of sine or cosine? One of those guys. I'm going to go with cosine. So D squared is equal to R squared plus R squared minus 2 R squared cosine of 120 degrees. Law of the cosines. And this is usually 0 because we got 90 degrees, you know? That's what you got. 2R squared times 1 minus the cosine of 120 whatever that is. I should know that. For shame. You guys tell me.
Why did you say 2r squared is 1?
What?
You said 2r squared is 1.
Well, I pulled out a 2r squared. Oh, cosine of 120 is minus a half, so this is 3 halves. If I didn't do that wrong. So I get 3r squared. So this is apparently a 3r squared. And there you have it. This is the relation between the radius squared and the velocity. Well, there's the relation between the velocity and the radius. You could solve for v if you want. I'd probably ask you to do that for the interest of my grading. Now, don't get lost in the algebra and trigonometry. The larger point here is just what? That it's going in a circle, so it's got mv squared over r as its net force, right? And that centripetal force has to be coming from gravitational forces. The part which is not centripetal cancel out. And this story repeats on each mass. Yep. Should we cancel out the r's? Oh, yeah, sure, why not? So v is the square root of gm divided by the square root of 3 times r. Want to know final question I put on a final once? And moons. Fix their mass, let the number go to infinity, describe the motion. The problem doesn't make sense. I posted on Stack Exchange. The guy explained why an infinity appears. My limit isn't quite right. I had a student kind of sort of solve it. Sort of. But he was a trigonometry ninja, that one. So, I mean, you can try. I might be able to find it. Give me a second. Well, my intuition, my reason for asking the problem was I thought it might be a way of like, maybe it was, I was thinking maybe I could think of a, like a, you know, like one of those, like a disk, like the rings of Saturn or something, as being like a continuum of moons, to understand like if it was rotating or something, but it did, something about it didn't make sense in the end. We do, no, not with n, but maybe with 2 or 3. I think I just promised you 2 at the start of this, if you haven't read between the lines yet. I did with 3, right? What would make it easier? 2. Although sometimes I slap a planet in the middle of it just to see if you guys are thinking. How would the planet change things? Then you've got a force of attraction towards the center planet too, right? It's been a few years since oh come on, no internet connection, I tell you. Uh-oh, I'd be careful. If I pull this too hard, I'll knock over the thing inside there. I don't want to do that. Yes, I would like you to connect. Please. All right. I've only asked about 20 questions, so it's fairly easy to figure it out. Ah, there it is. Infinitely many moons or one ring to bind them. All right. Here's the problem as it appears. Carnegie was a student in the class that had this problem originally. I said, the Carnegie clan makes its home on a distant planet. Oh, I put a mass M in the middle of it.
Did you make your title of Lord of the Rings?
Would I do that? That might have happened. Anyway, so, I imagine having N of them. Anyway, long story short, this guy basically proves that, and Min just about got to this, give or take. He proves that it goes to infinity. The velocity goes to infinity. Yeah. So my final exam question didn't make sense. Sadness. Don't worry, it didn't really hurt anybody's grade. But there you go. You can look at it if you want. I don't know. If you can find me on that silly Stack Exchange. It's not hard. All right, you guys have questions about your homework? We still have 18 minutes. What do you got questions? Yes, sir.
The question with the mud hitting the door.
Mud hitting the door.
That was the last question on the
Number 8.
Homework, angular motion.
Angular motion is that.
Which homework was it?
It's 10. And it's number 8.
was the last one.
Oh, okay. Cool. All right. We have a solid wood door, 1 meter wide, 2 meters high, hinged on one side, total mass 54 kilograms, initially open and at rest. The door struck at its center by a handful of sticky mud, mass blah, traveling perpendicular to the door at that just before impact. Find the final angular speed of the door. All right. Yeah, so this is conservation angular momentum problem. So you can imagine the door, right? And then right before it, there's a mass of sticky mud, right, with some velocity. So the question: what's the initial angular momentum of the mud? All right. So this is the pivot, right? Axis of rotation, right? What's the initial angular momentum of the mud just before it hits the door?
What's under the final momentum of the door?
Yes, but angular momentum will be conserved. And so the question is, what's the initial angular momentum? Once we know that, we can say that has to be equal to the final angular momentum. The final angular momentum, right, will be when the door is swinging with some final angular momentum, the mud will be stuck on it, right? And so like the moment of inertia will be the inertia for the door plus the inertia for the mud, right? And the final angular momentum will be I times omega f, where I is the final. So the initial angular moment, so the question is, but my point is angular momentum is conserved. L naught is equal to LF, all right? What is the initial angular momentum again? What's the inertia of the mud? What's the inertia of a point mass? mr squared, right? Which r, though? I mean, fine, I'll say mass the mud, which I need mud. This r, though, should be what? If this is half the radius of the door, right? That's where the mud hits right before it hits the door. It's at half the radius, right? That's the r I'm talking about. This